Hello there and welcome to Science for Sleep, where curiosity takes its time and answers arrive in no particular hurry. Tonight we're going to talk about something that's always there, always happening, but rarely questioned. It's the idea that everything, and I really mean everything, follows rules. Not just habits, like how your cat insists on knocking things off the table, but actual rules. Deep, unchanging, often invisible rules. The kind that govern how stars burn, how raindrops fall, and how your phone manages to light up when you touch the screen. We call them the laws of physics, and tonight we're going to quietly ask, what are they really? And why does everything seem to follow them so precisely? But before we go too far, maybe take a moment to get comfortable, adjust your blanket, breathe in slowly, and let the day soften around the edges. Whether you're winding down in bed, stretched out on the couch, or listening on a late-night walk, you've arrived at a strange little question tucked inside the universe itself. Why is everything so obedient? You might not think of the universe as obedient. It's vast, chaotic, unpredictable in many ways. Storms roll in when we least expect them, galaxies collide, socks disappear in dryers. But beneath all of that, under the storms and surprises and missing laundry, there's this strange, persistent consistency. Gravity always pulls, light always travels at the same speed. Atoms behave in exactly the same way whether they're in your cup of tea or drifting in space a billion light years away. There's an order to it, a regularity, almost as if the universe was handed a rule book and just stuck to it. This predictability is something we've come to rely on. Not just for science, but for everyday life. You turn on the faucet and water comes out. You drop a pen and it falls. You boil pasta and it softens. There's no need to wonder whether gravity is working today, or if heat will still flow from hot things to cold ones. We don't think twice about it. And that's kind of strange, isn't it? We assume these things will happen not because we hope they will, but because they always have. And that's where the idea of physical laws begins, not as a mystical concept, but as an observation, a noticing. People realised a long time ago that some things just always happen in the same way. Before anyone wrote down a single equation, humans were noticing patterns, the way the sun rose and set, the way shadows moved, the cycle of the seasons. These were the earliest hints that the world followed rules. They didn't call them laws of physics back then, but the idea was the same. Predictability, regularity, a kind of quiet order. Fast forward a few thousand years and we're no longer just watching shadows and stars. We're measuring, calculating, modelling. We're writing down laws, giving them names, fitting them into equations that can predict what will happen next. And we don't just mean next week or next year. Some of these laws can tell us how an asteroid will move 100 years from now, or how a star will die in a billion. We've built an entire civilization on this assumption that nature plays by consistent rules. Planes fly because the air behaves in predictable ways. Bridges stand because materials follow known stress and strain limits. Your phone connects to a satellite thousands of kilometers away because electromagnetic waves travel in a way we can trust. But here's the thing that keeps physicists up at night, or helps them fall asleep, depending on your perspective. Why? Why is the universe this way? Why is it so well behaved? Because it didn't have to be. Imagine a world where gravity sometimes pushed instead of pulled, or where light took different paths on different days, or where atoms occasionally forgot how to bond. A universe like that wouldn't just be confusing, it would be unlivable. Nothing would last. Nothing could form. No stars, no planets, no people. It would be like trying to build a sandcastle during a windstorm on a trampoline in the middle of an earthquake. Yet here we are, in a universe that doesn't just allow for structure and stability, it insists on it. This kind of order can feel comforting but also eerie. How does the universe know what to do? What keeps all these particles and forces in line? It's not like there's a cosmic traffic cop waving electrons into their orbits or keeping photons at the speed limit. These rules don't come with enforcement, they just are. And that might be the strangest part of all. No matter where you go in the universe, whether it's the inside of an atom or the outer edge of a galaxy, things behave in line with the same underlying principles. That's not just impressive, it's almost suspicious. Some scientists think of physical laws as descriptions of what things do. They're not commandments, not prescriptions, just summaries of observed regularities. When we say a ball will fall to the ground, we're not saying it has to. We're saying that it always does, and so we expect it to continue doing so. It's a model, a story we tell about the way things work, and so far, that story's been remarkably consistent. Others go further. They wonder whether these laws are baked into the very fabric of the universe, like a blueprint or a kind of operating system, something deeper than just description. Maybe these laws are the scaffolding that holds everything else in place, not just summaries of how things behave, but the reason things exist at all. Either way, we're dealing with something that goes beyond just observation. Physical laws aren't just about what happens, they shape what can happen. They define the boundaries of what's possible. There's no version of the universe, at least that we've seen, where the speed of a light is different, or where energy suddenly stops being conserved. And we've looked. We've peered into the cosmos with telescopes, probed the smallest particles with accelerators, and everything still dances to the same tune. That kind of consistency makes science possible. Without it, experiments wouldn't mean much. If the laws changed from place to place, or day to day, then results wouldn't repeat. Theories wouldn't hold. Engineering wouldn't work. The world would be chaos. The fact that we can send robots to Mars or land a probe on a comet speaks to just how deeply reliable these laws are. But reliable doesn't mean understood. There are still plenty of things we don't know. The laws we've uncovered might not be the final ones. There could be deeper rules hiding underneath. The laws of physics as we know them might be approximations, good enough for now but missing pieces. Maybe one day we'll find a more complete set, or maybe we'll discover that the laws themselves aren't fixed, that they can change, evolve, or emerge from something even more fundamental. That's the frontier of modern physics, not just discovering new laws, but asking why there are laws at all. Why is the universe lawful instead of chaotic? What selects the laws we have? Are they unique, or one of many possibilities? And if there are other possible sets of laws, do they play out somewhere else? In other universes, maybe, where the rules are different and everything follows a different script? For now, those questions don't have answers, but they do have a kind of quiet wonder to them. The same wonder that guided early astronomers watching the stars, or scientists scribbling formulas by candlelight. The sense that beneath the complexity and the noise there's a kind of structure, something persistent, dependable, familiar. We've spent some time marvelling at how everything seems to follow rules, the regularity of things, the predictability. It's natural then to ask, what do we actually mean when we say something is a law of physics? What makes a rule a law? And how is that different from a theory, or a principle, or just a good guess that happened to be right? In everyday life, we use the word law in a very specific way. It's usually tied to behaviour, what you're allowed to do, what you're not allowed to do, and what might happen if you break those boundaries. A speed limit is a law, so is paying your taxes. Those kinds of laws are created by people, enforced by systems, and can be changed, debated, even repealed. They come with consequences. Drive too fast, get a ticket, break the law, face the system. But physical laws aren't like that. They're not written down by committees. They're not enforced by any authority. There are no universal police officers out in space issuing violations to galaxies for colliding improperly. Physical laws aren't about what things should do. They're about what things always do. When scientists talk about a law of nature, what they usually mean is a statement, a description of a regular pattern in how the universe behaves, something we've observed to be true, over and over and over again. For example, Newton's law of universal gravitation says that every object attracts every other object, with a force proportional to their masses and inversely proportional to the square of the distance between them. That sounds technical, but it's just a fancy way of saying that gravity is predictable. You can measure it, you can calculate it, you can write it down and expect it to still work tomorrow, and it does. So in that sense, a law in physics is really just a summary. It's a shortcut. It captures what we've observed to be consistently true in a way that we can test, repeat, and apply. It's not a rule in the moral sense. It's not a suggestion. It's more like a statistical truth, a principle that, as far as we know, has never been violated. And that distinction matters, because when you hear the word law, it can sound final, permanent, unquestionable. But in science, nothing is ever above question. A law is only as good as its ability to hold up under scrutiny. If we find new evidence, reliable, repeatable evidence, that contradicts a law, then the law has to change, or at least be updated. And this brings us to another term you hear a lot in science, theory. And here's where things can get a little confusing, because in casual conversation, theory often means a guess, or an idea you're not sure about. Someone might say, that's just a theory, to dismiss something as speculation. But in science, a theory is much more than that. It's a well-substantiated explanation of some aspect of the natural world. It's a framework that makes sense of laws, observations, experiments, and predictions. It's not just a guess, it's the best possible explanation we have, based on all the evidence we've gathered. Take the theory of gravity. Gravity itself is the phenomenon. We feel it, we experience it, we measure it. Newton gave us a law that described it mathematically, and then Einstein came along and gave us a theory that explained it in a deeper way, as the curvature of space and time. The law told us what gravity did, the theory told us why. In that sense, theories and laws aren't in competition. One doesn't become the other, they do different jobs. A law describes, a theory explains, and both can coexist. You don't need to pick sides. Then there are other terms floating around too. Principles, postulates, hypotheses, models. Science can be a little messy with vocabulary sometimes, because these words often overlap, depending on how they're being used. A principle is usually a guiding rule or assumption, like the principle of conservation of energy, which says that energy can't be created or destroyed. A hypothesis is a testable idea, something you can check against observation. A model is a way of representing a system to make predictions or understand it better. And all of these, in one way or another, connect back to our desire to find order in the world. But at the centre of all of it is this core idea, that the universe behaves in consistent ways, and that those behaviours can be captured, at least approximately, in words and numbers. We watch, we measure, we look for patterns, and when the pattern is strong enough, when it holds true across many different cases, we might call it a law. That doesn't mean it's the final word. Newton's laws were once considered the foundation of physics, and they still work remarkably well for many things. But they eventually gave way to relativity and quantum mechanics when we started looking at things that move very fast or are very small. The new laws didn't replace the old ones. They refined them, gave them context, showed their limits. It's a bit like how maps work. If you have a map of your neighbourhood, it's incredibly useful. It shows the streets, the houses, the landmarks. It helps you get around. But if you try to use that same map to drive across the country, it won't help you much. It's not wrong. It's just not complete for the scale you're working with. Physical laws are like that. They're maps of how things behave, and as our view of the universe expands, sometimes the maps need updating. There's another wrinkle to this too. Sometimes what we call a law isn't really fundamental at all. It might just be a useful approximation of something deeper. For instance, Ohm's law in electricity describes how current flows through a conductor. It's handy, it works, but it's not a fundamental law of nature. It's more like a behaviour that emerges from deeper principles, like how electrons move and interact with materials. So not all laws are created equal. Some are foundational, tied to the deepest fabric of reality. Others are practical summaries. Both are useful, but in different ways. This brings up a subtle but important idea: emergence. Sometimes the rules we see aren't basic laws themselves, but the result of lots of simpler things interacting. It's like how traffic patterns emerge from the individual decisions of drivers, or how the behaviour of gases comes from billions of molecules bumping around. The laws we write down often describe the outcome, but not necessarily every tiny step that leads to it. And yet, despite all this complexity, the idea of laws still holds. There's something oddly reassuring about it. We live in a universe where the same experiment gives the same result over and over, where equations written down decades or even centuries ago still describe how things move, how they fall, how they combine, how they change. The language might evolve, the understanding might deepen, but the patterns remain. So when we say something is a law of physics, we're saying that it has earned its place, that it's been tested and tested again, that it describes reality in a way that's precise, useful, and, so far, unbroken. It's not sacred, it's not beyond revision, but it's a foundation, a step in the long climb toward understanding. And perhaps most importantly, it's shared. It doesn't depend on culture or opinion or belief. It's something that scientists in every country speaking every language can agree on, not because they were told to, but because the universe keeps showing it to them, in the same way every time. You've probably heard the story. A man sits beneath a tree, an apple falls, and somehow in that simple moment gravity's born. Of course, the real story is more complicated than that, but like many things in science, the myth sticks because it's clean, symbolic, and just believable enough to keep telling. The man was Isaac Newton. And what fell that day wasn't just fruit. It was a whole new way of thinking about the universe. Before Newton, people had ideas about why things moved and fell, but those ideas were more philosophical than mathematical. Aristotle, for example, believed that objects had natural places and tendencies. Heavy things wanted to fall, light things wanted to rise. It made intuitive sense, but it wasn't predictive. You couldn't use it to calculate how fast something would fall or how planets moved. It just sounded right. And for a long time, that was enough. Then came the scientific revolution. Thinkers started to ask not just what happened, but how precisely and why. They began to measure things, experiment, compare results. Motion, once explained by vague concepts like natural tendencies, started to be described with numbers, patterns, and eventually equations. Newton stepped into this moment and gave it structure. He didn't invent gravity, of course. Things were falling long before him. What he did was connect the dots, literally and mathematically. He realized that the same force pulling an apple to the ground could also explain the motion of the moon around the Earth, or the planets around the sun. That was the leap. It wasn't about apples, it was about unification. One rule, one law that applied everywhere. His law of universal gravitation was deceptively simple. Every object attracts every other object with a force. The strength of that force depends on two things: how massive the objects are and how far apart they are. The more massive, the stronger the pull. The farther apart, the weaker it becomes, and quickly. Mathematically, it falls off with the square of the distance. That's why you don't feel the gravitational pull of your bookshelf, even though technically it's pulling on you right now. This idea that gravity worked the same everywhere was revolutionary. Until then, people thought of earthly motion and celestial motion as two different things. Things down here fell. Things up there circled. Newton said no, it's all one system. The same law that makes an apple drop also keeps the moon in orbit. And with that, the heavens and the earth were united under a single rule. He didn't stop there. Newton also laid down 3 laws of motion, which described how objects behave when forces act on them. Taken together, his laws of motion and his law of gravity created a framework that could predict how everything moves. Balls, carts, comets, cannonballs, and for centuries it worked. Astonishingly well. In fact, for a long time people thought this was it. The universe was a machine. Everything obeyed predictable rules. If you knew the initial conditions, where things were and how fast they were moving, you could, in principle, calculate everything that would ever happen. Pierre-Simon Laplace, a French mathematician, even imagined a being, a kind of superintelligence, that, if it knew every detail of the present, could predict the entire future. That was the dream of determinism, a universe governed by laws like clockwork. But even within Newton's world there were questions. For one, what is gravity really? He could describe how it worked mathematically. He could predict its effects. But he couldn't explain what caused it. How could one object pull on another across empty space with no connection in between? It worked. But it was mysterious. Even Newton admitted that. Still, the success of his laws was undeniable. They could predict eclipses, guide ships, explain tides. They brought precision to fields that had once relied on rough guesses and rules of thumb. And more than anything, they showed that nature could be understood in terms of a few simple rules written in the language of mathematics. This was the beginning of what we now call classical physics. It set the stage for everything that followed. And even now, centuries later, Newton's equations are still used to send rockets into space, to model bridges, to describe everyday motion. They're not perfect. We've since discovered limits to their accuracy, but they're remarkably close, especially when things aren't moving too fast or getting too small. What's interesting, though, is how deeply this shaped our view of what a physical law should be. Thanks to Newton, we came to expect that laws would be simple, mathematical and universal. They'd apply everywhere, they'd be elegant, and maybe most importantly, they'd be something we could write down, something we could point to and say, this is how it works. And that idea stuck. Even as physics expanded into realms Newton never imagined, electricity, magnetism, quantum mechanics, the goal remained the same, to find the laws that govern each new domain, to express them clearly, precisely, and ideally with equations, to make sense of what happens, not just describe it. Newton's approach also introduced another important idea, that of initial conditions. Laws tell you how things change, but they need a starting point. If you know where something is and how fast it's moving, the laws can tell you what happens next. But without that starting information, the laws are silent. They don't predict everything from nothing. They need input. The rules are fixed, but the setup can vary. This becomes especially important later, when we start thinking about the universe as a whole. If there are laws and they're fixed, then the question becomes, why this setup? Why these initial conditions? It's a question Newton didn't try to answer, but one that still lingers. Another thing that came from Newton's framework was the idea of space and time as a backdrop. In his view, space was a stage, time was a universal clock, and the laws played out against that background. Everything had a position, a velocity, and a clear, measurable evolution. There was no fuzziness, no ambiguity, just cause and effect neatly laid out. For many scientists, that was deeply satisfying. It made the universe seem knowable, reliable, something you could, in principle, understand completely. And for a long while, it seemed like that dream might come true. The laws were being found, the gaps were closing. Nature, once mysterious and unpredictable, was revealing its code. But of course that wasn't the end of the story, it was just a beginning. Newton's laws worked astonishingly well, but they weren't the whole picture. They started to break down in certain conditions, when things moved very fast, or when objects became very small, or when gravity became extremely strong. And when that happened, physicists had to look deeper. The search for laws didn't stop with Newton. It only got more intense. Because once you believe that the universe plays by rules and that those rules can be known, you can't help but want to find the next one, to go further, to ask whether the rules themselves might change under certain conditions, or whether there's an even deeper rule behind them all waiting to be uncovered. And as we'll see, that search led to some strange and surprising places. Places where the old assumptions no longer held, where the simplicity gave way to uncertainty, and where the very idea of a law had to be re-examined. But the seed of it all, that trust in the regularity of nature, was planted long ago under the branches of a tree where an apple just happened to fall. The image of the universe as a clock didn't start with Newton, but he gave it gears. Once people saw how well his laws worked, how accurately they predicted motion, how neatly they explained orbits and collisions and tides, the metaphor of a clock became hard to resist. A clock is precise, it ticks, it moves in exact patterns. And most importantly, it doesn't make mistakes. Every tick leads to the next. Every gear turns the way it's supposed to. And for a while, that's exactly how the universe seemed. With Newton's laws, you could describe motion so well that it started to feel like there wasn't room for randomness. If you knew the position and velocity of every object in the universe, and you had enough calculating power, you could predict the future with perfect accuracy. Not just a few seconds ahead, but forever. You could roll time forward or backward, like spinning the hands of a watch, and the laws would still hold. It was a powerful idea, and to many it was beautiful. A universe that wasn't just functional, but orderly, consistent, mathematical. Nothing happened without a cause. Nothing escaped prediction. That wasn't just science. It was philosophy. It gave people a sense that the world made sense. And for a time, it seemed like that view might be complete. One law at a time, physics filled in the pieces, motion, force, energy, momentum. More laws were written, more equations. Nature was being carved into clear, sharp rules. The more we looked, the more precise it all became. This predictability extended into areas that once seemed too complex to measure. Planets were the obvious case. Using Newton's laws, astronomers could calculate their paths far into the future. But soon, engineers were applying the same ideas to machines, to bridges, to buildings. Everything physical seemed to follow the same rules, cause and effect scaled up or down. The clockwork view of the universe didn't just affect science, it seeped into culture. It changed how people thought about time, fate, even free will. If everything was following laws, what did that say about human choices? Were we just complicated machines, following internal mechanisms too subtle to measure? It was a question that lingered for centuries, and in some ways, it still does. But even clocks have their limits. They rely on precision, yes, but also simplicity. A clock doesn't need to know what its gears are made of, it just needs them to move. And that's where the metaphor starts to stretch. Because while the universe did seem to move with clock-like accuracy, it wasn't simple, not underneath. And the more we studied it, the more cracks appeared. Still, the clockwork view left a deep imprint. It gave science confidence. It showed that nature could be understood, that the behaviour of things was not arbitrary, but rule-based. And it encouraged a certain kind of thinking, the search for the next gear, the next equation, the deeper pattern. It also led to a belief in determinism. The idea that the future is fixed, at least in theory. If you knew everything about the present, you could work out everything that comes next. Not because the future is written, but because the laws of physics leave no room for surprise. The universe moves forward, tick by tick, and the ticks are predictable. But that view depended on some assumptions that would eventually be challenged. One of the biggest was time itself. In Newton's model, time was absolute. It flowed the same for everyone, everywhere. It was the master clock, the universal tick that kept all things in sync. And for a long time, that idea worked. It made sense. It matched experience. Time passed. Things changed. The laws described the motion. But as our instruments got better and our observations more precise, we started to notice something strange. Some things didn't fit. Light, for example, didn't behave the way we expected. Its speed was always the same, no matter how fast you moved toward or away from it. That didn't match the rules of classical mechanics. And it raised a question. If light isn't changing speed, then maybe time is. The gears of the universe were still turning, but they weren't doing it in quite the way we thought. The clock metaphor wasn't wrong exactly, but maybe it wasn't complete. Newton's laws had given us structure, but they hadn't given us flexibility. They didn't explain why some effects seemed to stretch or bend, and they couldn't account for the strange behaviour of things on very large or very small scales. So even as the universe ticked, scientists began to suspect there was more going on inside the gears. Not hidden pieces exactly, but hidden assumptions. The belief that time was universal, the belief that space was flat and constant, the belief that cause and effect always played out the same way. These ideas had worked for centuries, but now they were being tested. And soon someone would come along to test them harder than anyone had before, not by breaking the clock but by twisting it, showing that time didn't always tick the same. That motion could change how you experienced the flow of seconds. That space and time were not separate at all, but parts of the same fabric. When that shift happened, physics didn't collapse, it expanded. The laws were still there, but they bent. The universe still obeyed rules, but the rules were stranger than we thought. And so, the search continued. Not just for order, but for the deeper reasons behind it. Not just for predictability, but for the origins of the rules themselves. Because once you realise the gears might be flexible, you start to wonder who or what put them in place at all. When you look around, you don't see laws. You see things moving, changing, existing. Leaves fall, water boils, light streams through a window and lands in familiar shapes on the wall. Nothing in those moments looks like it's following a script. There's no floating label above the teacup saying thermal expansion in progress. And yet, something is guiding it all. The laws of physics are invisible not because they're hiding, but because they're not things exactly. They're relationships, patterns, connections between how things start and how they end up. When we call them laws, what we really mean is that we've noticed a certain behaviour always seems to happen the same way. It's not obvious just from looking. It takes careful observation, measurement, repetition. And over time, those patterns become familiar enough that we start to trust them. What's strange is how deeply these laws are embedded in everything, even though we can't point to them directly. They're not etched into atoms, they don't leave signatures in the sky, but they show up through consistency. Every time you let go of a ball, it falls. Every time you light a match, it burns in the same kind of curve. And if you repeat the same experiment under the same conditions, the same result appears again and again. It's that repetition that makes the pattern real. But that raises a quiet question. Why do these patterns exist in the first place? Why is the universe lawful at all? Some scientists think of these laws as discoveries. They're not created, but found, like uncovering fossils in rock. They were always there, just waiting to be noticed. Others wonder if they're more like inventions, tools we use to describe what we see. The universe does what it does, and we try to make sense of it by finding the most efficient ways to describe that behaviour. Maybe the laws aren't real in the way matter or energy is. Maybe they're just descriptions that work really well. There's even a third view, that the laws are neither discovered nor invented but emergent. They're not fundamental truths written into the universe's source code, but higher level rules that show up when things get complicated enough, like traffic patterns or weather systems, or the way flocks of birds turn together. No single bird is following a master plan, but the group together makes a pattern. If that's true, then maybe what we call physical laws aren't the foundation of everything, but the habits of a universe built from even simpler parts. Maybe the laws are a kind of cosmic routine, not enforced, not decreed, just inevitable. And yet, they seem anything but casual. The universe doesn't drift through random behaviours. It's structured. It has rules so reliable that we can use them to land probes on distant moons, to calculate the lifetime of stars, to predict the shape of a snowflake before it forms. Whatever these laws are, emergent, discovered or otherwise, they're astonishingly good at being consistent. That's why we call them fundamental. Not because they're the final answer, but because everything else seems to rely on them. Other patterns, other systems, all reduce back to a small handful of rules that sit underneath it all, quietly steering the universe. Conservation of energy, the inverse square law, the speed of light, equations that don't care where you are, or what language you speak, or whether you believe in them. They just work, and they work everywhere, not just on Earth, not just in our solar system, but in galaxies we've never visited, around stars we've only seen as faint blips in telescopes. The same rules, the same behaviour. It's hard to overstate how strange that is. You'd think that if the universe were just randomly assembled, you'd see all kinds of variation, different rules in different places, chaotic patches, exceptions. But no, we don't find patches of anti-gravity or places where atoms randomly stop following the electromagnetic force. Everything seems to follow the same invisible instructions, the same underlying logic. That uniformity gives science its power. It means the rules we test in a lab on Earth can apply to a star 10 billion light-years away. It means physics isn't just local, it's universal. That's not just useful, it's profound. But it also opens up deeper questions. If the laws are universal, then what determined them? Why these laws and not others? We can imagine different sets of rules. Universes where gravity repels instead of attracts, where time runs in loops, where electrons don't exist. Those universes wouldn't look anything like ours. They might not allow for stars or planets or chemistry or life. And yet, out of all the imaginable options, we ended up with this set. That idea has sparked decades of speculation. Are the laws we observe the only possible ones? Or are they just one version among many? Some theories in physics suggest that there could be countless other universes, each with different laws, different constants, different scripts. In that view, our universe isn't uniquely ordered, it's just one roll of the cosmic dice that happened to come up structured. Other physicists resist that idea. They think there's a deeper reason for the laws we have, not chance, but necessity. Maybe these laws are the only self-consistent ones. Maybe they're the only ones that don't contradict themselves or collapse into chaos. It's a kind of natural selection, but for rules. The ones that don't work don't survive. The ones that do become reality. Whatever the answer, it's clear that these laws aren't just decorations. They're not optional. They shape everything that happens and everything that can happen. And they do it silently, invisibly, relentlessly. They also raise a strange kind of trust. We trust that if we heat something up, it will expand. That if we let go of something, it will fall. Not because we believe in magic, but because we've never seen it not happen. It's like a contract the universe made with itself. A quiet promise to be consistent, even when no one is watching. And maybe that's what makes physical laws so powerful. Not just that they're invisible, but that they're dependable. Not just that they're mathematical, but that they work. And in a universe so vast and indifferent, that kind of reliability might be the closest thing we get to certainty, which makes it all the more curious that we can write these rules down, that we can express them in symbols and diagrams, and they continue to hold. The fact that the universe allows us to understand it at all is, in itself, part of the mystery. Are we discovering the logic of nature, or are we just building tools that fit what we happen to see? That question will keep coming up. But before we try to answer it, we should look at what happens when these rules take shape in equations, when invisible scripts become mathematical spells, and reality starts to obey the numbers. Somewhere in the middle of a notebook or scribbled on the corner of a chalkboard, or buried in a code library running quietly on a satellite, there's a short equation. It's just 3 letters and an equal sign, F equals ma. And somehow, that tiny bit of math is enough to describe how every object in the universe moves when pushed. This one equation, force equals mass times acceleration, has guided rockets, explained car crashes, helped build skyscrapers, and predicted the fall of a tennis ball. It's simple, compact, and surprisingly powerful. But like most of the so-called laws of physics, it's more than just a bit of arithmetic. It's a kind of spell. Not in the mystical sense, but in the way that saying it out loud, or writing it down, gives you control over something invisible. FIME didn't come out of nowhere. It's one of Newton's 3 laws of motion, the second one, technically, and probably the most widely used. It tells us that if you apply a force to something, the amount it accelerates depends on how much mass it has. More mass, more resistance. Less mass, easier to move. And if there's no force, there's no acceleration. Things in motion stay in motion. Things at rest stay at rest. The universe doesn't budge unless something pushes. What makes this powerful isn't just that it explains motion, it's that it does it in numbers. It lets you predict exactly how much force you'll need to launch a rocket or stop a bicycle. And once you know how to apply that force, you can shape what happens next. That's the essence of control, not just seeing a pattern, but using it. This is where physics starts to separate itself from pure observation. Lots of animals notice patterns. Humans take it a step further. We quantify them. We measure, record, calculate, and then we make predictions. We go from this usually happens to this will happen at this time in this exact way. And when it does, the confidence in the rule deepens. Equations like F or ma aren't just shortcuts. They're like keys that open parts of the universe. Once you know them, you can ask questions you couldn't ask before. What happens if we double the mass? What if we apply the same force over more time? You don't need to guess anymore. The math answers for you. And there are other equations like it, some just as compact, others sprawling and complex. Newton's law of gravity, Maxwell's equations for electromagnetism, Einstein's field equations, Schrödinger's equation in quantum mechanics. Each one is like a little piece of the user manual for reality, and each one, when applied, seems to work, across time, space, and scale. What's strange is how often these equations are simple. Not easy necessarily, but elegant, minimal, clean. There's a kind of efficiency in nature's logic. The same patterns show up in different systems. The same math works for fluids, galaxies, molecules, economies. It's as if the universe prefers certain structures, or perhaps it only allows them. That's one reason some physicists talk about the beauty of equations. Not in a poetic sense, but in terms of symmetry, simplicity, and power. The more concise the equation, the more surprising it is when it matches reality. It's not just about fitting the data, it's about expressing something fundamental with fewer pieces. There's something else too. When you first learn these equations, they can feel mechanical. They're tools, ways to solve problems. Plug in the numbers, get an answer. But over time, as you see them applied to real systems, they start to feel like something deeper. Not just instructions, but insights. They don't just describe how things move. They hint at why motion even has rules at all. And then there's the question of where they come from, not who wrote them down. Most were developed slowly, over years, through experiments and debates. But why they work at all? Why does force relate to mass and acceleration in this particular way? Why does energy behave according to this specific rule? Why are the laws of nature mathematical in the first place? Mathematics itself is abstract. Numbers aren't physical things, they're ideas. Yet somehow, when arranged correctly, they describe the world with astonishing accuracy. You can write an equation on a whiteboard, and it will predict what a planet does 1 billion kilometers away. The fact that numbers, human symbols, can do that is still unsettling to some scientists. Some believe the universe is inherently mathematical. That math isn't just a tool we use to describe reality, it is reality. Others think the match between math and physics is more about evolution. Our brains have evolved to notice patterns and develop systems that reflect the structures we find in nature. Math just happens to be the best tool we've found. Either way, the result is the same. The more we write down these equations, the more consistent they prove to be. And with each one, the sense grows that we're reading something, not inventing it. Like we're slowly decoding a script that was always there. But unlike the scripts we usually read, these don't have characters or dialogue. They have variables, constants, and operators. Instead of emotions and plot twists, they describe momentum, pressure, entropy, curvature. And yet, there's something dramatic in them, because they don't just explain what's already happened. They shape what can happen. They set the boundaries of possibility. Some equations only apply under certain conditions. They're approximations, useful but limited. Others, like the laws of thermodynamics, seem to apply universally no matter what. Physicists group them into different categories: empirical laws, derived laws, conservation laws, but at the core, they're all doing the same thing, connecting inputs to outputs, causes to effects. And that brings up another point, what we call causality. Most of these equations tell us that if we change one thing, something else will change too. Apply a force, you get acceleration. Add energy, the system shifts. The idea that changes have consequences is woven into the structure of the laws themselves, and that's one reason they're so useful. It also means they're falsifiable. If a law says that a certain input should always lead to a certain output, and one day it doesn't, then the law is broken, or incomplete. That's rare. But it happens, and when it does, it opens a door. New phenomena get uncovered, deeper rules are revealed, science moves forward. Some physicists chase that. They look for the edges, the cracks, the places where our current equations start to wobble. They're not trying to discard what works, they're trying to find what comes next. Because every equation, no matter how solid, is provisional. It's true until it isn't. And yet, even when replaced, the old ones often remain useful. We still use Newton's equations to design buildings and cars, even though we know they're technically wrong at relativistic speeds. They're not false, they're limited. And within their limits, they're still accurate. That's another reason these laws are powerful. They don't just describe systems, they scale, they adapt to context, they give us different lenses depending on what we're looking at. And even when we find better lenses, the old ones don't vanish. They become tools in a larger kit. Over time, that kit has grown. The equations have multiplied. And with each new law, the picture of the universe sharpens a bit. We start to see how heat moves, how light behaves, how forces combine, and always there's this quiet feeling underneath that we're not just cataloguing facts, but glimpsing something structural. Not just how the universe behaves, but why it behaves in any way at all. It's still strange sometimes to think that all of this rests on symbols, that the same squiggles you learn in school can unlock the behaviour of stars, atoms and oceans. But they do, and every time they work it reinforces the idea that we're tapping into something consistent. Not just clever models, but reflections of a deeper order. And that order doesn't seem to care whether we believe in it. It just keeps working. Equations hold, even when we don't understand why. The laws continue, even if no one's watching. And somewhere in the background, the universe moves forward, quietly following the spells we've only just begun to read. For a long time, science moved with the quiet confidence that the laws of physics were fixed. They described the world, they predicted what came next, and they didn't change. Laws, after all, are meant to be followed. That's what makes them laws. But over time, cracks started to appear. Not in the laws themselves, but in the way we understood them. Small mismatches between theory and observation. Exceptions that didn't quite fit. And when those mismatches showed up, The question wasn't whether nature had made a mistake. The question was whether our understanding of the laws was missing something. That's a key part of how science works. The laws aren't handed down as absolute truths. They're models built from evidence. They're tested, questioned, and, when necessary, adjusted. Not because nature is misbehaving, but because we're getting closer to how it really works. Sometimes those adjustments are small, a tiny correction here, a tweak there. Other times they lead to major shifts, like when Newton's laws couldn't explain the orbit of Mercury, how it seemed to wobble in a way no one could account for. The equations worked perfectly for every other planet, but Mercury was off, just slightly. For decades, astronomers tried to find an explanation. Some even suggested an undiscovered planet tugging at Mercury's path. But the answer came from somewhere else entirely. Einstein's theory of general relativity, published in 1915, changed the way we think about gravity. It showed that gravity wasn't a force in the way Newton had imagined it. Instead, it was the curvature of space-time itself. And when that new framework was applied to Mercury, the wobble vanished. The math worked. The law hadn't broken, we had simply found a better one. Examples like this show how laws don't really break, they evolve. And often, they evolve because our instruments get better. The more precisely we can measure the world, the more detail we see. And with that detail, sometimes the old rules need updating. Not because they were wrong, but because they were incomplete. There's also the matter of scale. Many laws of physics work incredibly well at the human level, at the speeds we travel, the sizes we interact with, the energies we use. But when you go beyond that, into the very large or the very small, the rules start to shift. Classical mechanics gives way to relativity and quantum mechanics. New behaviours emerge, and with them, new laws. This leads to a kind of patchwork. Different laws for different domains. Newton's laws for everyday motion. Maxwell's equations for electromagnetism. Schrödinger's equation for quantum systems. Each set of laws works within its range. Outside that range, it bends. It gives way to something else. And yet, there's a hope, a belief really, that beneath all these layers, there's a deeper unity. A set of principles that tie everything together. Physicists call it a theory of everything, not because it explains every detail of the universe, but because it unifies the forces and laws we already know. Gravity, electromagnetism, the strong and weak nuclear forces, all described by a single framework. It hasn't been found yet. But the search for it is one of the great ongoing efforts in physics. In the meantime, we keep working with what we have, and what we have mostly works. Incredibly well, in fact. Modern technology relies on laws that have held up under decades of testing. Quantum mechanics, for example, might seem strange and abstract, but it's also the foundation for semiconductors, lasers, and much of modern electronics. The laws are weird, but they're reliable. Still, the idea of a law bending, or seeming to, invites another kind of question. What if the laws themselves are not fixed? What if they can change over time? It's not something we've observed directly. But some theories in cosmology have suggested that the constants we take for granted, like the speed of light or the strength of gravity, might have been different in the early universe. Maybe the laws settled into their current form only after the Big Bang. Maybe they're not timeless truths, but the outcome of a process. If that's true, then the laws we know are local, in time as well as in space. They might be stable now, but that doesn't guarantee they were always this way, or that they'll stay this way forever. But even that idea doesn't mean the laws are breaking. It just means they have a context, a history, and science, as it always does, would adapt. It would shift the framework to account for the change. That's the difference between faith and science. Faith insists the rules are fixed. Science insists they're testable. That testability is what gives the laws their strength. Every law of physics makes predictions. If the predictions match reality, the law stands. If they don't, it gets questioned. And the more extreme the test, the more confident we become when the law holds. Sometimes, though, the problem isn't the law, it's us. Measurement errors, misinterpreted data, faulty assumptions. History is full of false alarms, apparent lawbreakers that turned out to be misunderstandings. The key is to check, again and again. And when something truly new appears, science expands to include it. There's also a category of situations where the laws seem to stop applying, not because they're wrong, but because our current understanding breaks down. Black holes, for instance, present a challenge. General relativity predicts that at the centre of a black hole, gravity becomes infinite. That's called a singularity. But infinities in physics usually signal that something's gone wrong with the math. It's not that the laws are failing, it's that we need new ones. Perhaps a better theory of quantum gravity that hasn't been built yet. The early moments of the universe raised similar issues. When the universe was incredibly dense and hot, the known laws don't quite work. Again, not a failure of nature, just a limit of what we currently understand. The boundary between what's explained and what's not is where science tends to grow. There's also a psychological angle. We like rules. We look for structure. So when something doesn't fit, it feels like a violation. But often, it's just a gap in knowledge. The universe isn't confused. We are. And as our understanding grows, the exceptions usually find their place. This doesn't mean everything can be explained right now. There are mysteries. Dark matter, dark energy, the exact nature of time. These are places where the current laws don't provide full answers. But the search isn't random. It's guided by what we already know. In the end, the laws of physics bend in two ways. They bend metaphorically when new theories improve on old ones, and they bend literally when we discover that the structure of space or time isn't what we thought. But they don't snap. They don't vanish. They evolve. They make room for more. And if we ever find that they've changed, that the constants are different, or that the rules themselves are shifting, then that too becomes part of the pattern. Because the point of science isn't that the laws are unchanging, it's that they're observable, they're repeatable, and they work, until we find a better way to explain why they do. If you look closely enough, symmetry shows up everywhere, not just in the shape of snowflakes or the wings of butterflies, but in the equations that describe how the universe works. It's more than just a visual pattern. In physics, symmetry means something deeper. It means that the laws don't change, even when you change your point of view. Rotate a circle, and it looks the same. Shift a repeating pattern to the side, and it still matches. Those are visual examples. In physics, you can do the same thing with time, space, motion. If the results of an experiment stay the same whether you do it today or tomorrow, that's symmetry in time. If it works the same here or over there, that's symmetry in space. And it turns out these symmetries aren't just aesthetic, they come with consequences. This idea became something far more powerful thanks to one person, Emmy Noether. She was a German mathematician working in the early 20th century, and her insight changed how physicists think about the structure of reality. Her theorem, quietly elegant and not especially long, revealed a hidden link between symmetry and conservation laws, and that connection became one of the foundational ideas in modern physics. Noether's theorem says this: every time you find a symmetry in the laws of physics, there's a corresponding conservation law. The universe doesn't just look orderly, it is orderly, and that order has rules. Take time, for example. If the laws of physics work the same today as they did yesterday, that's time symmetry. And what goes with that? Conservation of energy. Energy can change forms. It can turn from motion into heat, from electricity into light, but the total amount stays the same. Always. That rule doesn't come from nowhere. It comes from the fact that the laws don't care when something happens. Time doesn't change the rules, so energy doesn't disappear. Same idea with space. If the laws are the same here as they are 10 kilometers away, then you get conservation of momentum, and if the laws don't change when you rotate your system, if physics works the same in every direction, then angular momentum is conserved. Every spin, every orbit, every whirl of a galaxy keeps its motion, unless something external interferes. These links between symmetry and conservation aren't just theoretical. They're the backbone of modern physics. We use them constantly, when designing spacecraft, when modelling atoms, when simulating particles. The reason a satellite stays on course, the reason a skater speeds up when pulling in their arms, the reason a roller coaster can rise and fall without gaining or losing total energy, it all comes back to Noether's insight. And here's the surprising part. None of these conservation laws are obvious just by looking at the world. You have to dig. You have to translate the behaviour of systems into equations, and then look at how those equations behave under different transformations. It's like pulling on a thread and finding a whole structure hidden in the weave. The symmetry isn't just a bonus, it's the structure itself. This connection between symmetry and lawfulness is why physicists sometimes talk about beauty in equations, not in the sense of something being decorative, but in how the pieces fit together. There's a satisfaction when a law turns out to be invariant under a transformation, when the equation doesn't care what day it is, or where it's applied, or how fast you're moving. That kind of symmetry suggests something deep and universal. Not every equation has this, of course, and not every part of nature is symmetrical in the everyday sense. The universe itself has broken symmetries too. Not everything is balanced or mirrored. Matter outweighs antimatter. Some processes can't be reversed. Certain interactions behave differently depending on direction. But even these broken symmetries tell us something. They give structure to the asymmetries we do observe. They're part of the architecture. And at a deeper level, many of the most fundamental laws of physics are built entirely on symmetry principles. The standard model of particle physics, the theory that explains most of the known particles and forces, is constructed from symmetries. The forces we observe, the particles that interact, the ways they behave, all of that emerges from requirements about how the laws should behave under certain transformations. This approach to building physics, starting with symmetry and seeing what must follow, has become a guiding method. It's one reason why certain theories, like string theory, look the way they do. Not because we've measured everything they predict, but because the mathematical structure is so tightly constrained by symmetry that only certain kinds of behaviour are allowed. It narrows the possibilities. It focuses the search. And yet, none of this was obvious when people first started studying motion or force. The earliest laws of physics were empirical, built from careful measurement and intuition. It wasn't until much later that the hidden logic behind them began to emerge. Noether's theorem didn't rewrite those laws. It revealed why they work so reliably in the first place. This is what makes the symmetry-conservation link feel almost magical. It's not just that the laws of physics are consistent. It's that they're consistent because they don't play favourites. They don't pick a preferred time or place or orientation. And that impartiality generates structure. It's a strange kind of magic. Quiet. Logical. Built into the fabric of reality. And it doesn't require us to invent it. It just asks us to notice. Because once you see that symmetry implies conservation, you start looking for other symmetries. And when you find one, you ask, what is it protecting? What quantity is being held constant? And what does that tell us about the system? Sometimes the symmetry is subtle. Sometimes it's hidden. But when it's there, the consequences ripple outward. Not just for particles or planets, but for the entire shape of the universe. Symmetry helped us build quantum field theory. It helped us unify electricity and magnetism. It guides the search for new forces, new particles, and maybe even new dimensions. None of this means symmetry explains everything, but it's one of the clearest signposts we have, a way of navigating a universe that otherwise might seem random or chaotic. It tells us what can't happen, what must remain unchanged. and in a cosmos filled with motion and change, that kind of stillness matters. And so, just like that, an idea that began with quiet elegance in a lecture hall, one mathematician's proof tucked away in academic journals, ends up echoing through the foundations of physics. Noether's work didn't make the universe orderly. It showed us how that order reveals itself, and once we saw it, we couldn't stop seeing it. Because if symmetry leads to conservation, and conservation leads to stability, then maybe the stability we depend on, the dependable ticking of time, the reliable swing of motion, isn't just a coincidence. Maybe it's a feature of the deepest architecture we've ever glimpsed, and maybe the next laws we discover will be waiting quietly behind some symmetry we haven't yet noticed. It starts with something simple. You're on a train and it's moving smoothly. Inside, everything feels normal. You toss a ball up and catch it, and it lands right back in your hand. If the train's moving at a steady pace, there's no sense of motion at all. The laws of physics behave exactly the same way as if you were standing still. Now look out the window. The world outside is rushing past, but to you, nothing inside has changed. You could do the same experiment on a plane, or a ship, or a space station in orbit, and the ball would still fall into your hand the same way. That's the starting point of relativity. What's remarkable about this idea is how ordinary it feels. It just works. Motion doesn't seem to affect the basic laws of physics. But the moment you start asking how fast things are moving relative to something else, the whole picture starts to twist. The first clues came from studying light. By the late 1800s, physicists understood that light was a wave. What they didn't understand was how it moved. Waves usually need something to travel through. Water waves need water, sound waves need air. So it was assumed light must travel through something too. They called it the luminiferous ether, a kind of invisible substance that filled space. The idea was that light waves move through this medium, and that you could detect your motion relative to it. But when physicists tried to measure that motion, most famously in the Michelson-Morley experiment, they found nothing. No matter how they moved, light seemed to travel at the same speed in all directions. It didn't make sense. If you were moving toward a wave, it should reach you faster. If you were moving away, it should take longer. But with light, the speed didn't change. Not ever. That strange result set the stage for one of the most significant shifts in physics. In 1905, Albert Einstein proposed a new way of thinking about space and time. He started with two simple postulates. First, the laws of physics are the same in all inertial frames of reference. In other words, if you're moving at a constant speed in a straight line, the laws don't change. Second, the speed of light in a vacuum is the same for all observers, no matter how fast they're moving. Those two statements sound innocent, but together they completely reshape how we understand time, space, and motion. If the speed of light is always the same, then something else has to give. And what gives, according to special relativity, is your measurement of time and distance. Clocks tick differently depending on how fast you're moving. Rulers stretch or shrink depending on your speed. Events that seem simultaneous to one person might not be to another. Time and space, which we used to think of as fixed and separate, turn out to be flexible and linked. This leads to effects that sound like science fiction, but are very real. Time dilation, for instance. If you're moving very fast, time slows down for you relative to someone standing still. The faster you go, the stronger the effect. It's not just a matter of perception. Time actually passes more slowly for you. The same goes for length contraction. Objects moving at high speeds appear shorter along the direction of motion. And then there's the relativity of simultaneity. Two events that happen at the same time in one frame may occur at different times in another. These aren't just abstract concepts. They've been tested over and over with high-speed particles, atomic clocks on planes, and observations of cosmic rays. GPS satellites, for example, have to correct for relativistic effects constantly. If they didn't, their timing would drift by microseconds every day, which might not sound like much until you realise it would make your map wrong by kilometres. Special relativity changed the idea that space and time are passive backgrounds. Instead, they're part of a single framework, space-time. Events don't happen at places and times, they happen at coordinates in space-time, and those coordinates shift depending on how you're moving. But that was only the beginning. About a decade later, Einstein expanded his theory to include acceleration and gravity. That became general relativity. And with it came a much stranger, deeper idea. Gravity isn't a force in the traditional sense. It's the result of curved space-time. In this view, massive objects, like planets, stars and galaxies, don't pull on things. Instead, they bend the fabric of space-time around them, and objects move along the straightest possible path through that curved geometry. It's a bit like rolling a ball on a trampoline that's been distorted by a heavy weight in the middle. The ball curves, not because something is tugging on it, but because the surface it moves through is bent. This idea, that gravity is geometry, has been tested in dozens of ways. It predicted things that Newton's laws couldn't explain, like the bending of light around massive objects, or the way time slows down in strong gravitational fields. It predicted gravitational waves, ripples in space-time itself, which were finally detected a century later in 2015. And here's where the laws start to stretch, because in relativity, the laws of physics still hold, but they're not absolute in the way we once thought. They adapt to context. The same laws apply, but the quantities involved, time, distance, velocity, change depending on the observer. The laws are still universal, but the experience of them is personal. It's not that physics is subjective, it's that reality is more flexible than we expected. Each observer gets their own version of space and time, and the laws work within those frames. It's as if the universe recalculates for each point of view, making sure everything stays consistent, even if it looks different. And yet, despite all this bending and warping, the structure holds. Objects still obey the rules. Energy is still conserved. Momentum still matters. Causality is preserved. Effects still follow causes. It's just that the coordinates we use to describe those relationships are no longer fixed. This flexibility doesn't mean chaos. It means precision at a deeper level. Relativity isn't about uncertainty. It's about correcting for assumptions that only work at slow speeds and weak gravity. Once you adjust those assumptions, everything clicks back into place. The elegance of this system is one of the reasons relativity is so admired. Not just because it's accurate, but because it makes space and time dynamic. They're no longer passive containers, they're participants. They stretch, they respond, they shape and are shaped by mass and energy. And that idea opens the door to even more questions. If space and time can bend, what's their limit? Can they break? Can they fold back on themselves? Does the shape of space-time set the shape of the laws, or the other way around? Those questions move us into the territory of black holes, wormholes, and the edges of the observable universe. But before we go that far, it's worth holding on to this. The laws of physics don't stop working when space bends or time stretches. They flex with the fabric they describe. They adapt, and in doing so they show just how sturdy they really are. In the everyday world, things make sense. You throw a ball, it arcs through the air. You flip a switch, the light comes on. You pour tea into a cup, and the liquid fills it predictably. Cause leads to effect. Motion follows rules. Measurements make sense. This is the comfort of classical physics. But zoom in far enough, down to the level of atoms, electrons and particles too small to see, and that comfort starts to disappear. In that tiny world, the rules change. Outcomes become uncertain. Positions get fuzzy. Particles act like waves, and waves act like particles. And instead of clear, predictable motion, we get probability. We enter the realm of quantum mechanics, where the universe doesn't run like a clock, it rolls the dice. It didn't start that way. Early in the 20th century, physicists were simply trying to explain a few odd observations, things like the way atoms emitted light, or why electrons didn't spiral into the nucleus. They weren't trying to overturn reality, but the more they looked, the more reality refused to play by classical rules. One of the first signs was the photoelectric effect. When light shines on certain materials, it can knock electrons loose, but it only works if the light has enough energy, no matter how dim it is. That made no sense under classical wave theory. Einstein explained it by saying that light comes in discrete packets, quanta, each with a specific energy. That was a big leap. It meant light wasn't just a wave, it was also a particle, and that opened the door to quantum theory. From there, things got stranger. It turned out that not just light, but everything behaves both like a particle and a wave. Electrons can interfere with themselves, creating patterns as if they're rippling through space. But when you measure them, they land in a single spot, like a particle. This duality, sometimes wave, sometimes particle, isn't just confusing, it's fundamental. Then came the uncertainty principle. Formulated by Werner Heisenberg, it says you can't precisely know both the position and the momentum of a particle at the same time. The more accurately you know one, the fuzzier the other becomes. It's not a limit of our instruments, it's a feature of reality. Particles don't have exact positions and speeds at the same time. They exist in a haze of possibilities. The mathematics that describes this haze is called the wave function. It doesn't tell you where a particle is, but where it's likely to be. It evolves according to an equation, the Schrödinger equation, that determines how this cloud of probabilities changes over time. But when you make a measurement, the wave function collapses, and you get a definite outcome. Not all possibilities, just one. Why does this collapse happen? No one really knows. There are interpretations, theories, guesses. Some physicists say the wave function is just a tool for predicting outcomes and that collapse is a kind of mathematical shortcut. Others believe it's a real physical process. Some suggest that all the possible outcomes actually happen in separate branching universes, and we only observe one. That's the many worlds interpretation. It sounds wild, but it fits the math. What's clear is that quantum mechanics works astonishingly well. It predicts the behavior of atoms, molecules, semiconductors, superconductors. It explains why the sun shines. It's behind the design of every transistor, every laser, every computer chip. It doesn't just describe the microscopic world, it defines it. And yet, it breaks many of our intuitions. In the classical world, if something isn't visible, it still has a location. In the quantum world, a particle can be in a superposition, existing in multiple potential states at once, until measured. Like Schrödinger's famous cat, alive and dead in the same sealed box until you open the lid. Entanglement makes things even stranger. Two particles can become linked in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he wasn't pleased. It seemed to violate the idea that information couldn't travel faster than light. But experiments have confirmed entanglement again and again. It's real. It doesn't allow faster than light communication, but it does challenge our ideas about separation and independence. So where do laws fit into all of this? If outcomes are probabilistic, is there still order? The answer is yes. But it's an order of probabilities, not certainties. Quantum laws don't say what will happen. They say what might happen and how likely each outcome is. You can't predict where a single electron will land, but you can predict the shape of a whole cloud of electrons. And those predictions match reality with incredible accuracy. This kind of lawfulness is subtler than in classical physics. It requires letting go of determinism, the idea that the future is fixed if only you knew all the variables. In the quantum world, the future is a range of outcomes, weighted by probability. It's not chaos, it's structured uncertainty. And yet, even within that uncertainty, there are rules. Conservation laws still apply. Energy, momentum, charge. These quantities remain consistent even in quantum systems. Symmetry still matters. Noether's theorem still holds. The laws haven't vanished, they've just changed shape. Quantum mechanics also introduced something new to physics, the observer. Not in a mystical sense, but in a mathematical one. The act of measurement affects the system. Observation and outcome are linked. That doesn't mean consciousness controls reality, but it does mean that interaction changes the probabilities. And that raises difficult questions about the boundary between system and observer, between potential and actual. It also challenges our idea of objectivity. If the system behaves differently when it's measured, then where does the measurement begin? Is it the instrument, the experimenter, the environment? Those questions are still being debated. They cut deep into the foundations of physics, but for all its strangeness, quantum mechanics is stable. The dice may roll, but the rules of the game don't change. The equations are fixed, the structure is solid, and the probabilities, though uncertain in the moment, add up over time to clear and reliable behaviour. Enough to build computers, enough to model chemical reactions, enough to understand stars. The universe doesn't abandon its laws at small scales, it just rewrites them. What looks like randomness isn't disorder. It's a different kind of order, one that operates in shadows, in averages, in wave functions and entangled states. And through all of it, the laws persist, not in firm declarations, but in statistical guidance, not in certainty, but in possibility. Because even when the universe throws dice, it does so with a loaded hand. The odds are always set. The rules are always there. And somehow, even in that haze of probability, the shape of the world continues to hold. In a universe filled with motion, change, collision and chaos, there's something quietly reassuring about the idea that certain things never disappear. No matter how fast objects move, how violently stars explode, or how unpredictably particles interact, some quantities remain the same. They might shift from one form to another, spread out or condense, appear to vanish, only to show up somewhere else. But the total never changes. This is conservation, and it's one of the most consistent, dependable patterns the universe offers. If the laws of physics are the rules of the game, then conservation laws are the accounting system. They're the part that tracks everything. Keeping a cosmic ledger, not just watching what goes in and what comes out, but making sure the total matches, every time, everywhere. Take energy. It's not always obvious where it is or what form it's in, but the total amount is constant. When you push a swing, you're converting chemical energy from your body into motion. As the swing arcs upward, that motion becomes potential energy. As it falls back, the cycle reverses. Energy moves around, bounces between forms, but never vanishes. The same goes for momentum. Push off a wall in space, and both you and the wall move apart. Not because you pushed hard, but because the system had to stay balanced. Your forward momentum is matched by the wall's motion in the opposite direction. The total stays the same. Even if the system expands or the forces change, the total momentum remains. Conservation of charge works similarly. You can't create electric charge from nothing. You can separate positive and negative charges, move them around, recombine them, but the net total doesn't change. It's a built-in rule. Even in particle interactions where matter is created or destroyed, charge is preserved. These laws show up everywhere, in mechanics, in thermodynamics, in quantum physics. They're not suggestions or trends. They're absolute as far as we can tell. Every experiment we've ever done has respected them. And when something looks like it doesn't, it usually means we've missed a piece of the system. Sometimes that missing piece becomes a discovery. When radioactive particles decayed and the energy didn't seem to add up, physicists didn't throw out the conservation laws. Instead, they proposed a new particle, the neutrino. It carried away the missing energy. The conservation law held, and the neutrino turned out to be real. The books balanced. They always do. You can think of these laws as constraints. They don't tell you what will happen, but they limit the range of what can happen. Like a budget, they force trade-offs. You can gain energy here only if you lose it there. You can't invent momentum out of nowhere. The system must remain honest, even when the individual parts are doing something wild. There's a certain elegance in that. In a universe where things are constantly in motion, these laws give structure. They prevent the impossible. They define what's allowed. And in doing so, they give us tools for prediction, for design, for understanding. Even the first law of thermodynamics, the conservation of energy, rests on this principle. It's what makes engines work. It's why we can calculate orbits, model ecosystems, and build electronics. Energy might change form, mechanical, thermal, chemical, electrical, but the total remains, always. This reliability extends into quantum mechanics too. Particles might behave unpredictably, but the underlying accounting still holds. A quantum particle might appear to pop into and out of existence, but it does so within strict rules. Borrowed energy must be paid back. Borrowed time must be short. The uncertainty principle allows flexibility, but not debt. The ledger stays clean. There's also conservation of angular momentum, an often overlooked but deeply important principle. It's why spinning ice skaters speed up when they pull in their arms, why collapsing stars spin faster as they shrink into neutron stars. The total angular momentum of an isolated system stays constant, even as the configuration changes. In the big picture, these conservation laws help explain the stability of galaxies, the motion of planets, the structure of atoms. They show up at every level, from a marble rolling across a table to the fusion reactions in the sun, to the most delicate interference patterns in a particle detector. They also help test new theories. If a proposed idea violates conservation, it's almost certainly wrong. That makes these laws more than just tools, they're filters. Anything that contradicts them is rejected or forced to explain how the rule is preserved in a hidden way. And then there's entropy, the second law of thermodynamics. It's not quite a conservation law, it's more of a direction. It says that in a closed system, disorder tends to increase. Energy becomes less useful. Systems drift from order to chaos. You can't build a perpetual motion machine. You can't extract unlimited work from a single source of heat. The universe has rules not just about totals, but about flow. And while entropy increases, the total energy still remains. It just spreads out, gets harder to use. Like trying to clean up glitter, still present, just no longer helpful. Well, all of these rules, conservation of energy, momentum, charge, angular momentum, aren't just convenient. They're fundamental. They come up again and again across every domain of physics. And when we find new forces or particles, one of the first questions we ask is, what's conserved? What's held constant? It's a way to find structure inside complexity. Sometimes a new conservation law hints at something deeper. Symmetry, for example. As we saw earlier, every conservation law connects to a symmetry in nature. Time symmetry means energy is conserved. Space symmetry means momentum is conserved. These aren't coincidences, they're consequences, and they tie the entire framework of physics together. They also provide reassurance. Even when the universe seems unpredictable, when particles behave oddly, or galaxies collide in violent dances, the totals hold. The system remains closed, consistent, balanced. You might not know what will happen next, but you know that whatever it is, the math will still add up. And this goes beyond theory. Engineers rely on conservation laws to build everything, from engines to aircraft. Chemists use them to balance reactions. Doctors use them to understand how radiation interacts with tissue. Wherever systems are moving, changing, or exchanging anything, energy, force, charge, conservation laws are running in the background. So the next time you throw a ball or ride a bike downhill or notice steam rising from a kettle, remember that there's a balance underneath. A quiet, invisible ledger keeping track. It doesn't tell you what to do, but it tells you what's possible. And in a universe full of movement and change, that kind of structure is more than useful. It's essential. You can change the language, you can change the units, you can even change your frame of reference. But some numbers don't budge. No matter where you are, how fast you're going, or what kind of particle you're measuring, these values remain the same. They are constants, fixed quantities that quietly anchor the laws of physics. And without them, none of those laws would mean anything at all. Constants aren't just background settings. They're the actual values the universe has chosen, for reasons we still don't fully understand. The speed of light in a vacuum, the gravitational constant, Planck's constant, the charge of the electron. Each one is a kind of cosmic fingerprint, unchanging, universal, and crucial to how everything works. Start with the most famous, the speed of light, usually written as c. It's about 290,792,358 meters per second, and it's not just fast, it's the fastest. Nothing with mass can ever reach it. And more than that, it's a boundary. It shows up not just in relativity, but in all kinds of equations across physics. C defines the structure of space-time. It sets the upper limit for how information and cause can move. In many ways, it defines causality itself. Then there's G, the gravitational constant. It's what makes Newton's law of universal gravitation, and later, Einstein's field equations actually work. It tells us how strong the force of gravity is between two masses at a given distance. Without G, we'd know gravity exists, but we wouldn't know how much pull it exerts. And once you start dealing with massive objects like stars and planets, that number becomes essential. Too small, and gravity becomes a whisper. Too large, and everything collapses. Planck's constant, h, lives in the quantum world. It's incredibly small, around 6.626 guessed 10 to 34 joule seconds, but it defines the scale at which quantum effects become noticeable. It sets the size of the steps in energy levels. It explains why electrons in atoms occupy discrete shells rather than swirling around at random, and it's central to the uncertainty principle, to the energy of photons, to quantum tunneling, to everything that makes the quantum world so unlike our everyday one. You've also got the elementary charge, E, which is the magnitude of the electric charge carried by a single proton, or, equivalently, the negative of the charge of an electron. It's not just a bookkeeping detail. This constant governs how particles attract or repel, how atoms bond, how circuits carry current. It's baked into electromagnetism at every level. And then there's E0, the vacuum permittivity, and N0, the vacuum permeability. Together they describe how electric and magnetic fields propagate through space. They're hidden inside Maxwell's equations, the ones that describe how light and radio waves move, and they're linked directly to c, the speed of light itself. You can derive c from them. These aren't just random numbers, they're part of the same web. All of these constants are measured, not derived. We didn't calculate them from first principles. We found them by experiment, carefully over time improving the precision, checking the results. They're input, not output. We plug them into the laws and the laws work. Without them, the equations are just empty forms. Some constants are dimensionful. They have units. You can express them in meters per second, or joules, or coulombs. Others are dimensionless. These are especially intriguing. One of the most famous is the fine structure constant, usually written as A. It's approximately 137, and it measures the strength of the electromagnetic interaction. It's a pure number with no units. You could be in a different universe with different scales, and it would still be 137 if the physics were the same. That kind of number raises big questions. Why that value? Why not suck on 150 or 112? We don't know. We know it works. We can build everything from chemistry to quantum electrodynamics on it, but we don't know why it's that particular number. And the same goes for the other constants. They're measured, they're fixed, but their origins remain one of the great open questions in physics. Could they be different? That's one of the more uncomfortable possibilities. In theory, a universe with slightly different constants might not work at all. Stars might not form, atoms might not hold together, life might be impossible. It's hard to test that idea, we only get to study this universe, but simulations suggest that even tiny changes to these numbers could make everything collapse, burn out, or drift apart. Some theories propose that these constants are not fixed by logic or necessity, but by chance. In a multiverse, there might be countless other universes, each with different values. We live in one where the numbers happen to support complexity, and that's why we're here to notice them. That's called the anthropic principle. It doesn't explain why the constants are what they are. It just says we shouldn't be surprised that they support life, because if they didn't, we wouldn't be here. Other physicists are less comfortable with that idea. They hope there's a deeper reason, an underlying theory that explains why each constant has the value it does. Something more fundamental than observation. But for now, that theory doesn't exist. What we do know is that these constants show up everywhere. You can't do real physics without them. They're the fixed points in the equations. They're what lets us turn a general law into a specific prediction. And as our measurements get more precise, the constants hold steady. They're also part of how we define other things. In fact, in recent years, the International System of Units, SCI, was redefined based on fixed values of certain constants. The kilogram, for example, is now defined using Planck's constant, the meter by the speed of light. This reflects a deeper shift, from using physical artifacts to using physical laws as standards. The constants are the reference, and that's maybe the most interesting thing of all. We use these constants to anchor our definitions of space, time, mass, and energy, but they themselves aren't defined by anything. They're just there, embedded in the machinery, woven into the equations, silent, unchanging numbers that the entire universe agrees on. It's a kind of cosmic loyalty. These values don't fluctuate, don't shift from one galaxy to another. They don't care about gravity, temperature, or scale. They just are. And somehow, from that quiet reliability, all the movement, colour, complexity, and change we see in the universe emerges. Constants don't explain why the universe is the way it is, but they define how it stays that way. And in a system built on motion, that kind of stillness might be the most important part of all. It's easy to think of physical laws as just facts, as if they've always been there, etched into the fabric of the universe like carvings on stone. They seem eternal, unchanging, immune to context. The speed of light, the law of gravitation, the conservation of energy, these aren't just patterns we've noticed. They feel like rules the universe must follow. But once you start asking where those rules come from, the ground under your feet starts to shift. Are these laws built into the structure of space and time? Are they consequences of something deeper? Or are they just the best approximations we've managed to piece together so far? Human tools that work, but not because they're ultimate truths. There isn't one clear answer. But the question itself, where do physical laws come from, sits right at the edge of physics, philosophy, and logic. And every attempt to answer it has taken us somewhere unexpected. Some physicists think of laws as discovered. In this view, the universe is a kind of machine, running on a set of rules, and our job is to uncover those rules by careful observation. We don't invent gravity. We measure it. We don't create the conservation of momentum. We verify it through repeated, consistent results. Laws here are part of the architecture, fixed, absolute, and waiting to be found. Others take a more cautious view. They argue that laws aren't so much discovered as constructed, not in the sense of being made up arbitrarily, but as models we've built to describe what we observe. The universe doesn't come with a manual, so we write down equations that match behaviour, refine them over time, and call them laws once they consistently predict results. In this view, The laws are human interpretations, summaries of observed regularities, not prescriptions for how things must behave. And then there's a third possibility, that laws aren't either discovered or constructed, but emergent. Maybe the universe isn't following a rulebook at all. Maybe it starts with something far simpler, some core ingredients, a few fundamental conditions, and the laws we observe arise naturally from the interactions between those parts. Like a murmuration of birds creating shapes that no individual bird is planning. Like traffic patterns that form without anyone directing them. Complexity from simplicity. If that's the case, then the laws of physics might not be fundamental. They might be statistical, they might be approximate, and they might depend on scale. At one level of reality you get quantum field theory, at another thermodynamics. Both work, both are essential, but neither is the absolute base. There's also the question of why the laws take the particular form they do. Why inverse square forces? Why the fine structure constant? Why does gravity pull instead of push? You can imagine other rules, ones that still produce something, but not this. Our laws allow stars to form, chemistry to exist, biology to emerge. Other rules might not. This gets into deep territory. Some physicists turn to the idea of a multiverse, countless universes, each with different laws or constants, each a different outcome of initial conditions. In that framework, we don't ask why the laws are the way they are. We just note that we're in a universe where they allow observers like us to exist. It's not an answer, exactly, but a filtering mechanism. We couldn't be here if the laws were incompatible with complexity. Not everyone is satisfied with that. It feels too much like resignation. Others hope for a final theory, a single, elegant framework from which all known laws emerge, a unifying set of equations that explain not just gravity or electromagnetism, but why those forces exist at all, why space and time take the forms they do, why particles have the masses they have. It's a high bar, and we're not there yet. What we do have is a collection of models that work extremely well. General relativity, quantum mechanics, the standard model of particle physics. Each one describes part of the picture with extraordinary precision, but they're not seamless. General relativity and quantum mechanics don't mesh. There are gaps, tensions, places where we know our laws aren't the final answer. And that's important, because every law we've ever written down came from noticing something regular, then testing it, then refining the description. No law started perfect. Even Newton's laws, once seen as the pinnacle of physical understanding, had to be updated to fit the behaviour of light or the bending of space-time near a black hole. So in practice, laws are always provisional. They're as true as we can tell given current evidence. And yet, despite that humility, they work. They power technology. They explain stars. They make predictions we can test again and again. They hold up. That tension, that the laws are both deeply mysterious and also incredibly useful, is part of what makes physics compelling. We don't know where these rules come from, but we do know they seem to apply everywhere, with no exceptions we can find. And that brings up another layer. Why is the universe lawful at all? Why isn't it random or chaotic or ruleless? That's not something physics can answer directly. It assumes lawfulness as a starting point. It builds on the idea that cause leads to effect, that outcomes can be measured, that patterns repeat. If the universe weren't that way, physics wouldn't work. Nothing would. So maybe asking, where do laws come from, is like asking why water flows downhill. Maybe it's built into the nature of existence. Or maybe there's a reason we haven't seen yet. Maybe the laws we know are just the surface of something deeper. A logic that runs beneath space-time, beneath matter, beneath even the idea of cause and effect. What's clear is that the more we learn, the more the question stays open. And that's not a failure. It's a sign that the laws, whatever they are, still have more to teach us. Not just about the world, but about what it means for anything to have rules in the first place. You can be standing on a sidewalk watching a ball bounce, and the rules that govern that motion The arc it makes, the time it takes to fall, the speed it rebounds, are exactly the same rules that describe what's happening on a distant moon, or in the tail of a comet, or in a galaxy whose light has taken 1 billion years to reach us. That kind of consistency feels normal because we're used to it, but it shouldn't be taken for granted, because it raises a quiet but deep question. Why do the laws of physics work everywhere? The universe, as far as we can tell, has no central control, no cosmic traffic light making sure every region plays by the same rules. There's no enforcement mechanism, no physical barrier stopping one pocket of space from behaving differently than another. And yet, across distances so vast that light itself struggles to cross them, everything seems to follow the same playbook. There are galaxies on the far edge of what we can see, places we'll never reach, filled with stars we'll never visit. And when we look at the light they send us, it obeys the same equations that govern the glow of a candle here on Earth. The same redshift that applies to light leaving a flashlight applies to the light stretching out as the universe expands. The same principles of motion, the same electromagnetic behavior, the same atomic structure. They all hold everywhere we've looked. This universality is one of the strongest assumptions in physics. It has to be. If the laws weren't consistent, then every experiment would be a one-time event. We couldn't generalize. We couldn't build theories. We couldn't rely on evidence gathered in one place to make predictions somewhere else. The entire method of science depends on repeatability, and repeatability assumes sameness across time, across space. But why should the universe cooperate? One answer is built right into the structure of the laws themselves. Many of our physical theories start with an assumption called homogeneity and isotropy. Homogeneity means the universe is the same in all locations. Isotropy means it looks the same in all directions. These aren't conclusions, they're starting points. Not because we know they're true everywhere, but because they match what we observe so far, and because they let us build equations that can be tested. And the tests have come. Cosmic microwave background radiation, the afterglow of the Big Bang, shows the same patterns no matter which direction we look. The distribution of galaxies, the behavior of light, the properties of matter across huge distances all seem to follow the same rules. If there are regions where the laws change, they're too far away to see and too subtle to leave a trace. There's also a deeper idea underneath all this: symmetry. When a system has symmetry, when it doesn't change under certain transformations, it leads to conservation laws, as we've seen. But it also implies uniformity. If the laws work the same over time and space, then you don't need to update them as you move. That kind of symmetry is a mathematical statement, but it has physical consequences. It allows laws to propagate without needing to be enforced. You don't need to keep reminding gravity how strong it's supposed to be. Once the constant is set, it holds. Once the mass and distance are known, the same equation applies. It's not a rule that spreads. It's a relationship that simply is. But that opens another layer of the question. How are the laws encoded into the universe? Are they part of the structure of space-time itself? Are they embedded in fields that fill space? Or are they descriptions of patterns that just happen to emerge over and over? Some theories, especially in modern cosmology, suggest that the early universe locked in its laws during the first tiny fraction of a second after the Big Bang. As energy cooled and particles formed, the properties of those particles and the forces between them stabilized, the constants settled, the equations found their shape. And once set, those patterns stretched outward with space itself. They didn't have to travel, they expanded with the universe. If that's the case, then the laws don't apply everywhere because they spread. They apply everywhere because everywhere came from the same place. The entire observable universe was once compressed into something very small, and everything we see now, every atom, every photon, every galaxy, is part of the same unfolding. That would explain the consistency, but it still doesn't explain why those laws, or why they're stable. It doesn't tell us whether they could vary somewhere else. and it doesn't prove that the laws are universal forever, just that so far they haven't let us down. Some physicists have wondered whether the laws really are the same everywhere. Maybe there are tiny variations in the constants of nature, subtle shifts in the behaviour of particles across time or distance. Astronomers have looked for signs of this, in the light from distant quasars, in the ratios of elements from ancient stars, but so far nothing conclusive. The numbers hold. There's also the idea that the laws might be local expressions of something deeper, that what we call physical laws are effective behaviours that emerge from underlying systems we don't fully understand. In that case, the reason they work everywhere might be because the underlying system is everywhere. The real law would be something beneath our current theories, something that isn't written in equations but in structure. What's striking is how little tweaking it would take to make the universe unrecognisable. If gravity were slightly stronger, stars would burn too fast. If the fine structure constant were different, atoms wouldn't form stable bonds. If the mass of the neutron were just a bit larger or smaller, the chemistry of life wouldn't work. The fact that all these pieces line up not just once, but across the entire observable cosmos, feels uncanny. Maybe it's coincidence, maybe it's selection, or maybe it's a clue. What we know, with confidence, is that the laws we've written down are the same ones that govern the fusion in the heart of the sun, the fall of a pebble in your hand, and the light echoing from the edge of the visible universe. They don't need to be sent anywhere. They don't travel or get installed. They're embedded, not in one region or another, but in the very logic that space and time follow. Wherever those two exist, the laws apply. So when you push a pencil across a table, you're not just dealing with a local interaction. You're seeing the same physics that shapes galaxies, collapses stars, and set the motion of planets long before life began. The fact that it feels normal is a kind of illusion. It's not normal, it's astonishing. And the further we look, the more we see that nothing changes. Redshifted or not, stretched by expansion or curved by gravity, the signals still obey the rules. The same equations that describe what happens here describe what happens billions of light years away. And unless something breaks that pattern, the universe gives us no reason to expect anything different. Not yet. We like things to fit. We build theories, make predictions, and feel a quiet satisfaction when the pieces line up. When the apple falls, the pendulum swings, the photon hits the detector exactly where the equation says it should. But sometimes, quietly, inconveniently, something doesn't match. A measurement comes in just slightly off. An outcome resists the prediction. It might be a margin of error thing. It might be a fluke, or it might be something deeper. That's the problem of exceptions. The history of physics is filled with these small inconsistencies, little anomalies that didn't go away. Mercury's orbit, for example, for decades, its precession, the slow rotation of its elliptical path around the sun, didn't quite match what Newton's laws predicted. The difference wasn't huge, but it was persistent. People tried to explain it with hypothetical planets or unseen matter. None of that worked. Then Einstein came along, and general relativity resolved it instantly. The exception wasn't an error, it was a hint. Exceptions are like friction in the gears of a machine. They tell you that your model isn't complete, that there's something in the system you haven't accounted for, and in the right context they lead to breakthroughs. The discovery of neutrinos came from an energy discrepancy in radioactive decay. The expansion of the universe came from galaxies moving away faster than expected. Cosmic microwave background radiation was discovered because a couple of radio engineers were trying to eliminate a stubborn hiss from their antenna. Some exceptions are real discoveries, others aren't. Some turn out to be experimental error, statistical noise, or artifacts of flawed measurement. In those cases, the law holds and the violation fades. But how do you tell the difference? How do you know when an exception means something? Usually it comes down to persistence. Real anomalies tend to stick around. They show up in different places under different conditions. The muon's magnetic moment, for example, has long shown a tiny mismatch with theoretical predictions. It's not dramatic, but it's precise, and that mismatch hasn't gone away. New experiments keep refining the measurement, and the theory side keeps digging for an explanation. Maybe the models are missing something. Maybe there's new physics there. Maybe it's just a correction waiting to be found. This is part of the tension in physics. We want to believe the laws are universal, clean, complete. But the moment we treat them as untouchable, we risk missing the very thing that could move them forward. Because science doesn't grow by sitting still. It grows by noticing the places where expectation and reality don't align, and that noticing takes patience. Not every wobble in the data means the law is broken. Sometimes it just means we're looking too closely at noise. Good science knows the difference between a pattern and a coincidence. It's why replication matters. Why independent confirmation is a bedrock principle. An exception that's real should show up again, and again, and again. But even then, exceptions don't always overturn the laws. Often, they expand them. The laws of classical mechanics didn't vanish when relativity arrived. They were absorbed as special cases, approximations that work at low speeds and weak gravitational fields. Quantum mechanics didn't destroy thermodynamics. It explained it. Exceptions don't always tear things down. They often show where to build next. Sometimes, though, the problem isn't with the theory, it's with the boundary between what's being described and what's being assumed. For example, conservation laws apply in closed systems, but if you're not careful, you might be looking at an open one. Energy might appear to vanish, when in fact it's escaping the system you're observing. The law didn't fail, the setup was just incomplete. That's why physics is always tied to conditions. No law stands in isolation. Every equation carries assumptions about scale, temperature, pressure, speed, surroundings. And when those assumptions break down, so does the applicability of the law. Not because nature is misbehaving, but because you're trying to use a wrench on a screw. And yet, despite all that, the number of true exceptions, the places where the universe actually deviates from what we expect, is remarkably small. Most of the time, the laws hold. They work. They predict correctly across experiments, systems, environments. And that's what makes the anomalies so powerful. Because they're rare, and rare things stand out. This is what separates physics from belief. Laws aren't protected. They're not sacred. They're provisional. Even the most solid ones are always waiting to be tested again. And when an exception appears, the job isn't to dismiss it. It's to study it. Patiently, skeptically, with the understanding that it could be either a window or a smudge on the glass, and sometimes the law itself bends to let the exception in. Take the discovery of parity violation in the weak nuclear force. For decades, it was assumed that nature didn't distinguish left from right. That mirror symmetry held in all physical processes. Then experiments showed that certain reactions favoured one direction. Symmetry wasn't absolute. The law adjusted. Those moments don't happen often, but when they do, they reshape the field. They take what was assumed and show that even assumptions need limits. And what emerges afterward isn't chaos, it's a better map. So the problem of exceptions isn't a flaw in science, it's one of its engines. It's how the system tests itself, how it stays honest, how it opens space for change without collapsing into uncertainty. In the end, what we call a law in physics is always a statement of what we've observed so far, repeatedly, reliably, under many conditions. It's not a guarantee, it's a structure. And when something pushes on that structure, the response isn't denial, it's investigation. Because sometimes, the crack isn't a weakness, it's a hinge. And on the other side of that hinge might be a deeper, stronger, more complete understanding of how the universe actually works. Imagine a universe that exists but has no rules, no gravity, no conservation of energy, no defined speed of light or mass or direction. Things move, or maybe they don't, but nothing governs that motion. Outcomes don't repeat. Causes don't lead to effects. Patterns, if they appear, don't last. You can't build a theory because nothing stays the same long enough to measure it. No clocks tick, no atoms hold, no concepts like temperature or pressure make sense because there's no framework for interaction, no laws at all. Could such a universe exist? And if it did, would it mean anything? This is more than a thought experiment. It gets at something deeper. Is lawfulness necessary for existence? Or can there be a kind of reality where things are without any rules at all? When we talk about the laws of physics, we're talking about the regularities we can observe. Gravity pulls, light travels at a constant speed, energy changes form, but never disappears. These laws are the basis for everything we understand about the cosmos. They allow prediction, replication, explanation. But they're also tightly tied to something we often take for granted: stability. Law implies regularity. Regularity implies time. Time implies change that can be measured, compared, ordered. Remove the laws and that whole structure begins to fall apart. Without laws, what's left? If a tree falls in a forest that's governed by no physical laws, the question isn't just whether anyone hears it, it's whether falling even means anything. Whether the tree can exist as a coherent object for more than a moment. Whether the atoms making up the trunk stay bound, or whether their behaviour changes from one instant to the next. Whether time itself has meaning in a world with no consistent progression. In practice, everything we know depends on laws, not necessarily the exact equations we've written down, but the idea that there are consistent behaviours over time and space. That energy today will behave the same as energy tomorrow. That mass has a consistent response to force. That information doesn't vanish or appear without cause. Even our ability to reason about anything depends on that kind of consistency. Logic itself is a form of rule following. If contradiction is allowed, if something can be both true and false in the same sense at the same time, then reasoning collapses. Nothing holds. So it may be that lawlessness isn't just unusual, it may be meaningless, or at least unobservable, because observation depends on comparison, and comparison requires a stable backdrop. A frame of reference, a way to distinguish before from after, this from that. If a universe changes its rules every instant, then nothing can persist long enough to be noticed. Not by an observer, not even internally. In that sense, law might not just be a feature of the universe, it might be a precondition for any universe we could talk about. Some cosmologists wonder whether there could be regions of reality, perhaps far beyond our own universe, where different laws apply, or where laws emerge more slowly, or where they never emerge at all. In those places, maybe nothing coherent forms, maybe matter doesn't stabilize, maybe space and time don't unfold. Maybe there is something, but not in any way we'd recognize. From our perspective, existence seems inseparable from structure. We see particles forming atoms, atoms forming molecules, molecules forming matter. At every level, the patterns are built on rules, and those rules are testable, measurable, universal, as far as we can tell. We've never seen an exception where the rules simply turn off, and yet the idea of a lawless reality lingers, because it forces us to confront what we mean by law. Is a law a command, a constraint, a description of observed behaviour, or is it something deeper, something the universe can't not have? If laws are emergent, if they form out of underlying dynamics, then maybe there was a time when they didn't exist, a pre-law phase before the universe cooled or stabilized. Some theories of quantum gravity suggest this. Imagining a state before space and time as we know them, where nothing yet behaved predictably, not chaos exactly, more like a canvas still wet. If that's true, then lawfulness might be like crystallization, a phase change, a moment when the system locked into a pattern and that pattern spread, hardened, scaled. The laws became what we call reality. But even then there's structure underneath, something that allows possibility, some kind of meta-logic from which regularity can emerge. So even in the most abstract cases, it's hard to imagine a complete absence of all rule. Even randomness requires a framework. This leads to a strange but compelling idea. That law might be inevitable. Not in the sense that this particular set of laws had to happen, but that some kind of consistent behaviour had to settle in. Because without it, there's nothing to observe, no patterns, no information, no interactions, no time. So if a tree falls in a lawless forest, it may not fall at all. It may not stand. It may not be. Not because we can't see it, but because without laws the very idea of tree loses meaning. So does falling, so does the forest, and so does the question. In the end, this isn't about trees, or forests, or sounds. It's about what makes a universe coherent. And the answer, as far as we can tell, is that lawfulness isn't just one feature among many. It's the foundation that makes all other features possible. Not a rule that was imposed from outside, not a script that was written before the curtain rose, just the quiet, stubborn regularity that turns chaos into structure, possibility into prediction, and silence into the kind of world where questions like this can even be asked. For a long time, physics felt like a story that was settling in. Newton's laws laid the groundwork. Maxwell unified electricity and magnetism. Thermodynamics gave structure to heat and energy. Then came relativity, reshaping gravity, and quantum mechanics, opening the strange world of the very small. And with each new chapter, the laws didn't break the old ones. They expanded them, refined them, made them fit into a broader picture. But then something happened. Two of the most successful, most deeply tested theories in all of science, general relativity and quantum mechanics, turned out to disagree. Not in the details, not in the margins, but in their foundations. They both work. They both predict correctly. But they don't speak the same language, and no one has fully figured out how to translate between them. This is what happens when laws conflict. Not because the universe is being inconsistent, but because the frameworks we use to describe it start pulling in different directions. They apply to different regimes. They rest on different assumptions, and when you try to force them together, at the edges, in black holes, in the early universe, they won't quite fit. Relativity describes gravity as geometry. It treats space and time as a smooth, continuous fabric, bent by mass and energy. It's a deterministic theory. Given initial conditions, the future unfolds precisely. It works beautifully at large scales, stars, galaxies, the structure of the cosmos. Quantum mechanics, on the other hand, deals in probabilities. It's built for particles and forces at the smallest scales, where outcomes aren't certain and where randomness plays a fundamental role. Its world isn't smooth, it's granular, fuzzy, indeterminate. Fields fluctuate. Particles pop in and out of existence. And yet, both are right. Both have been tested again and again, with experiments reaching astonishing precision. GPS satellites rely on relativistic corrections to stay accurate. Particle accelerators rely on quantum field theory to predict the results of high-energy collisions. Neither theory has failed. Neither is wrong. But put them in the same room, and they argue. Nowhere is this more obvious than inside a black hole. Relativity predicts the existence of a singularity, a point where gravity becomes infinite and space-time curves to a place the equations can't handle. But quantum mechanics can't make sense of infinities. It expects limits, behaviors, constraints. A singularity isn't just a weird outcome, it's a sign that the model has broken down. Similar tension shows up when trying to describe the earliest moments of the universe. During the Big Bang, the density and temperature were so extreme that both quantum effects and gravity were dominant. But our current theories can't describe both at once. We can run the equations up to a certain point, and then they stop being meaningful. This conflict isn't just an academic problem, it's a crack in the foundation. We have two rulebooks, both correct, that can't be reconciled. And that's not how laws are supposed to behave. So what do you do when the laws disagree? One option is to look for a deeper theory, something that contains both relativity and quantum mechanics as special cases. String theory is one candidate. It proposes that particles aren't points, but tiny vibrating strings, and that their vibrations produce all known forces and particles. String theory naturally includes gravity, and it operates at quantum scales. But it's mathematically complex and lacks direct experimental confirmation. Another idea is loop quantum gravity, which tries to quantize space-time itself. Instead of treating gravity as a smooth curve, it describes space as made of discrete chunks, loops of geometry woven together. It's a very different approach from string theory, but it shares the same goal: unify the laws. Some physicists suggest that our entire approach might need to change, that trying to force gravity into a quantum framework, or quantum mechanics into a relativistic one, misses something essential. Maybe there's a different way to think about space, time, and matter. Something more radical, something that changes the questions entirely. But until that deeper framework appears, until the conflict is resolved, we're left with patchwork. We use quantum mechanics when dealing with particles and fields. We use general relativity when dealing with stars and planets, and we avoid the places where both would be needed at once. This isn't failure, it's boundary work, and it's not new. Thermodynamics and statistical mechanics were once separate. Electricity and magnetism were once unrelated. It took time to connect them. It took patience. And the conflict between relativity and quantum mechanics may simply be the next bridge waiting to be built. In the meantime, physicists keep pushing the edges, looking for inconsistencies, unexplained effects, anything that hints at a deeper unity. Places where the laws break down, or just blur, are the best places to learn. They're the fault lines where new understanding can form. And it's worth remembering that a conflict between laws doesn't mean the universe is breaking its own rules. It means our descriptions are incomplete. The underlying system still behaves consistently. It's our models that haven't caught up. When laws conflict, it doesn't mean truth has failed. It means the picture is still in progress. And that maybe, somewhere just beyond the reach of our current frameworks, there's a larger logic waiting, one that can hold both order and uncertainty, curves and quanta, gravity and chance in the same equation. The phrase sounds dramatic, almost too ambitious to be real. A theory of everything, not just a set of rules for particles or fields, not just a framework for galaxies or black holes, but one single, coherent explanation for all physical phenomena. Everything from the way quarks combine to form protons, to the way space bends around a planet, to the way time flows when you pour coffee. It would be the ultimate compression of knowledge, a single set of principles that underlies all other laws. Why would we even want that? Part of it is philosophical. Physics has always been about finding the unity behind the complexity. We used to think heat, motion, and energy were separate things until thermodynamics connected them. We thought electricity and magnetism were distinct until Maxwell's equations joined them. The success of physics again and again has been its ability to unify, not by making things simpler, but by revealing that apparently separate behaviours are just different aspects of the same structure. A theory of everything would take that idea to the limit. It would be the ultimate unifier. But there's more to it than that. Because right now, the two best theories we have, quantum mechanics and general relativity, don't play well together. As precise and powerful as they are, they operate in different domains and break down when applied at the same time. If we want to understand what's happening at the core of a black hole, or at the moment of the Big Bang, we need a framework that can do both. That's where a theory of everything comes in. not just as a grand idea, but as a practical necessity. We need something that can describe how gravity behaves at quantum scales, how space-time interacts with the smallest particles, how information is preserved, or not, when matter crosses the event horizon of a black hole. The search for this theory isn't new. In some ways, it's been underway since Einstein. He spent the later part of his life trying to unify gravity with electromagnetism, two forces that seemed like they should be part of the same picture. He didn't succeed, partly because quantum theory was still developing, partly because the unification turned out to be harder than anyone expected. Since then, the quest has grown more sophisticated. String theory became one of the leading candidates, proposing that all particles are just different vibrational modes of tiny, one-dimensional strings. The math is elegant. It naturally includes gravity, and it offers a way to connect all the known forces and particles under a single framework. But it requires extra dimensions, more than we can observe, and its predictions are hard to test directly. Loop quantum gravity offers a different approach. Instead of treating particles as fundamental, it tries to quantize space-time itself. No strings, no extra dimensions, just a new way of thinking about geometry and scale. It's elegant in a different way, but faces its own challenges. Other approaches exist too. Causal dynamical triangulations, emergent gravity models, even ideas that space-time is built from quantum information. None are complete, none have been experimentally confirmed, but all are aimed at the same thing: to stitch the universe back together so our equations don't have to choose between describing the very big or the very small. But the deeper you go into the idea of a theory of everything, the more subtle the questions become. What exactly are we trying to explain? Is it just a mathematical framework that unites the forces? Or are we also trying to explain the values of the constants, the speed of light, the gravitational constant, the fine structure constant? Do we want to know why this universe, with these particles and these laws, came into being, or just how those pieces fit together? Some physicists argue that a theory of everything is a misleading term, because it won't explain everything, not in the everyday sense. It won't tell you how a hurricane forms, or how a brain generates thought, or how societies evolve. It won't replace chemistry or biology or psychology. It will just provide the deepest possible foundation, the base layer of physical law that everything else builds on. In that sense, a theory of everything is like the operating system of the universe. It won't tell you what every app does. It won't predict every user's actions. But it will define the architecture that makes all of it possible. And there's another possibility, that there is no final theory, that the universe isn't built on a single, elegant principle, but on layers. Effective theories stacked on other effective theories. Laws that hold only in certain regimes. Models that work not because they are fundamentally true, but because they are useful at certain scales. In that view, unification may be a mirage. Something we want because simplicity is beautiful, not because nature owes it to us. Still, the drive is there. The desire to see beyond the fragments, to find not just patterns, but the pattern behind the patterns. We're not just collecting rules, we're asking what holds them together. And even if the theory never comes, not in our lifetime or in any, just reaching for it reshapes the way we understand the world. It forces us to ask sharper questions, to test more rigorously, to look at the boundaries where our current theories strain and falter. Theory of everything doesn't mean end of science. It would be the beginning of a new kind. Once you have the base code, you can ask better questions about the higher levels, about emergence, complexity, life, consciousness. So we keep going. Not because we expect a perfect answer tomorrow, but because every step toward unification reveals more about how astonishingly coherent the universe already is. And even if the final theory turns out to be stranger or simpler or more abstract than we imagined, it will still be built on the same idea that's guided physics from the start. That underneath all the motion, all the fields, all the particles and space and time, there is something that holds, a rule, a rhythm, a reason, something that binds it all together, not to satisfy curiosity, but because that's how this reality works. And the closer we get to it, the more everything else starts to make sense. We don't know if there are other universes, but the idea won't go away. It comes up in physics, in cosmology, in philosophy, even in particle theory. Not because we want it to be true, but because the math keeps opening doors we didn't expect. Because when we try to answer questions about why our universe has the laws it does, the constants it does, the structures it does, we keep running into a strange possibility. That maybe these features aren't universal. Maybe they're local. Maybe the laws we see are just one example of how a universe can be. It's hard to imagine. Our universe feels complete. It has gravity, quantum fields, thermodynamics, conservation laws, all seemingly woven together. You can trace particles back to their origins, link equations across space and time, and find remarkable consistency. But that consistency doesn't necessarily prove uniqueness. It just proves that this system works. So the question isn't whether the laws of physics are coherent. They are. It's whether they're inevitable, and the more we look, the harder that is to claim. Start with the constants, the speed of light, the gravitational constant, the strength of the electromagnetic force. These aren't derived from theory. We measure them, plug them into equations. They're inputs, not outputs. We don't know why they have the values they do. We just know that if they were even slightly different, the structure of matter, chemistry, stars, and life might not hold together. That tuning feels suspicious. It's called the fine-tuning problem. Why do the numbers line up just right? Why is the universe so precisely set up to support complexity? Some physicists argue that this isn't a coincidence, it's a selection effect. We observe this universe because it's one of the rare kinds that can produce observers. In that view, there may be other universes, maybe countless ones, with different laws, different constants, different particle families, most of them sterile, lifeless, chaotic, but not this one. This idea gets formal support in certain versions of inflation theory. Inflation suggests that in the early moments after the Big Bang, space expanded faster than light, exponentially, chaotically. And if that expansion happened in patches, with different patches freezing out with different properties, then each region could become its own universe, with its own vacuum state and its own laws. You end up with a multiverse, not just in the science fiction sense of parallel worlds, but as a natural consequence of high-energy physics. Each universe has different parameters, like rolling dice with slightly different physics each time. Quantum mechanics even gives us another angle, through the many worlds interpretation, where every possible outcome of every quantum event exists in its own branching timeline. String theory takes it further. It doesn't just allow multiple universes, it predicts an enormous number of possible ones. The theory contains a landscape of possible solutions, each corresponding to a different vacuum, different particles, different constants. We're talking about numbers like 10,500 possible universes, each one with its own version of laws. We don't know if any of those actually exist, but mathematically they're valid. And this leads to a strange realization. Maybe the laws of physics aren't fundamental. Maybe they're environmental, like weather patterns shaped by geography, or dialects shaped by history. What we call the laws may just be the result of how our particular bubble of reality cooled, condensed, and stabilized. If that's true, it changes how we think about physics. The goal wouldn't be to explain why the constants are what they are, but to understand the landscape they came from, to find the rules behind the rules. A deeper theory that doesn't just describe this universe, but the space of possible universes. It also redefines what explanation means. Instead of one final fixed theory, we might have a kind of probability map. A way to say, in most universes this feature is rare, but in a few it shows up. And then we find ourselves in one of the few. This kind of reasoning is controversial. It's hard to test. Some argue it's not science unless it makes predictions we can confirm. Others argue that if the theory naturally produces a multiverse, we have to follow it, even if most of those universes are forever out of reach. And yet, there is evidence that pushes us in this direction. The uniformity of the cosmic microwave background, the scale and flatness of the universe, the statistical patterns we see in large-scale structure. These aren't proof of other universes, but they're hard to explain without inflation, and inflation naturally leads to a multiverse. So could other universes have different laws? Yes. That's not just possible. It's the default in most models that allow multiple universes, and if so, those laws could be drastically different. Maybe no gravity, maybe no strong nuclear force, maybe only 2 spatial dimensions, maybe nothing like matter at all. Or maybe subtle changes, like a slightly stronger electromagnetic force which prevents hydrogen atoms from forming, or a slightly weaker gravity which means stars never ignite. A universe can exist mathematically without being complex enough to build structures. And if most of the multiverse is like that, then it's no surprise we ended up here. Because here things can notice they exist. None of this means other universes do exist. But the idea that our laws are not unique, that they're one possibility among many, is gaining ground. Not because we want it to be true, but because the alternative is to believe the universe had to be this way, with no deeper reason. And physics is always looking for reasons, so we keep looking, not for proof that other universes are out there, but for signs that our laws are just a corner of something bigger. And if that turns out to be true, then what we call fundamental physics may someday be just one chapter in a much larger story. One where the rules change, the players change, and the game keeps unfolding in ways we're only just beginning to imagine. Some laws seem permanent. They don't wobble, don't shift, don't fade. Gravity pulls. Light moves at a fixed speed. Particles behave predictably, at least statistically, according to rules that we've written down in equations and tested in experiments across centuries. These laws feel like they've been written in ink. Crisp, finished, unalterable. But then there's another feeling, that maybe not everything is quite so final, that some rules might only be local, temporary or emergent, that maybe they started as soft pencil marks, sketches made in the early days of the universe, erasable, revisable, not yet committed to permanence. And that leaves us with a question. Are the laws of physics written in ink or pencil? It's not rhetorical. Physicists ask this kind of thing all the time, even if they phrase it more technically. Are the constants of nature truly constant? Is the structure of space and time fixed, or does it evolve? Are the laws of physics absolute, or do they arise from deeper, possibly shifting principles? The assumption for most of modern science has been ink. If a law holds here, it should hold everywhere. If it's measured today, it'll match tomorrow. And so far, the evidence supports that view. The constants we've measured, the charge of the electron, the strength of gravity, the speed of light, haven't changed, not even slightly, not across time, not across space. We've looked. Light from distant galaxies travelling billions of years behaves just as expected. The fine structure constant measured in ancient starlight shows no sign of drift. Atomic clocks compared over decades remain consistent down to astonishing precision. It all points to permanence. But permanence in physics doesn't mean unchallengeable. It means so far. And there are places where so far isn't far enough. The early universe, for instance. Right after the Big Bang, the conditions were extreme. Densities, temperatures, and energies far beyond what we can recreate. Some theories suggest that in those conditions the laws we know now weren't fully in place. Maybe the forces we now treat as separate, gravity, electromagnetism, the strong and weak nuclear forces, were once unified, governed not by 4 laws but by one, and as the universe cooled, that unity fractured. the laws we know crystallized out of something simpler or stranger. In that view, what we call fundamental laws are actually frozen choices, patterns that settle during a phase transition, like water turning to ice. And if the early conditions had been different, maybe the laws would be too. Not completely random, but contingent, shaped by the unfolding. That's pencil. Laws that form through evolution. Not erased easily, but not etched from the start. There's also the idea of emergence, that the laws we see at our scale, the ones that govern particles, forces, motion, aren't the base layer of reality. They're approximations, behaviours that come out of deeper structures, like temperature emerging from the movement of molecules, or pressure arising from collisions. We can measure those things, describe them with laws, but they aren't fundamental. They're summaries. If space and time themselves are emergent, as some quantum gravity models suggest, then even general relativity, our best theory of space-time, would be an emergent law. Useful, precise, powerful, but not written in ink. More like a sketch that holds under most conditions, but not all. And then there are ideas that push further. What if constants like the fine structure constant or the cosmological constant do vary, very slowly, very subtly across the history of the universe? Some theories propose this. They haven't been confirmed, but they haven't been ruled out entirely either. We need even more precise measurements, better instruments, more time. Some physicists don't like that idea. They prefer the universe to be written in ink, fixed, clean, eternal. Because change introduces ambiguity. If the rules evolve, how can we ever be sure of anything? But physics isn't about comfort, it's about what matches reality. And if reality is more flexible than we thought, the framework needs to adapt. It's also possible that the universe uses both. Some laws might be fixed, baked into the deepest structure of what can exist. Others might emerge as consequences shaped by initial conditions, symmetry breaking, or statistical regularity. Ink and pencil working together. And maybe that's the real answer. That the universe isn't a finished document. It's a living draft. Some lines have been inked. Others are still being adjusted. And what we call laws are the parts we've learned to read, the parts that hold steady across everything we've tested, for now. It's tempting to imagine that someday we'll find the final theory, the master equation, the deepest logic, the true ink beneath all the layers. Maybe we will. Maybe we won't. Maybe there is no final theory, only deeper levels of pencil, sketched finer and finer, never quite closing the loop. What matters isn't whether the laws are permanent in some absolute sense. What matters is that they've been consistent enough for life to form, for stars to shine, for planets to orbit, for questions to be asked. Consistent enough for us to do science at all. So maybe the better metaphor isn't a book written in ink or pencil. Maybe it's a story being told. One scene at a time with enough structure to keep it moving and enough room for surprise. A story we're still inside, still listening to, still learning how to read,